So, hi, I'm Suzanne Staggs from Princeton, and I want to thank the Quantum Gravity Society for inviting me to this stimulating and extravagant meeting in one of the most beautiful cities in the world. And I want to describe the marrying of experimental techniques, some of which have their own resonances to current preoccupations in the quantum mechanics world. So the marrying of those techniques to a possibly quixotic search for the oldest possible gravitational waves that have yet been proposed to exist. So at first, I fretted over this fitness of the word married or marrying in the title of the conference. But upon reflection, indeed, the intersections between gravity and quantum mechanics that are evidenced in the existence and form of the cosmic microwave background that Slava was just talking about, they're deep, they're complicated, they're primordial, they're difficult to explain, and perhaps they're unknowable. So yeah, that's a lot like a marriage. So. Okay, so the montage of images here is meant to evoke some key aspects of the cosmic microwave background, or CMB as we usually call it. So measurements, I guess I could point, but then only one screen will see it. Measurements from Penzias and Wilson in the 60s indicated a seemingly isotropic, meaning without inhomogeneity, thermal bath of photons that was suffusing the universe. And then interpretation of the CMB as being leftover or relic radiation from plasma in a much earlier epoch, before gravitational instability, that process of the rich getting richer that Slava described, had fully transformed the initially really tiny density fluctuations into the huge peaks that we call home today. So that interpretation of the CMB as being relic radiation soon followed after that initial detection in the 60s. And then its thermal nature was confirmed resoundingly, first by the UBC rocket, and then subsequently by the satellite COBE in the late 80s. So that's depicted here. And then the minuteness of its anisotropies, which again, Slava was mentioning, but also their interesting power spectrum were in clear evidence by the 2000s. Okay. Right, so here's another visualization of the CMB, this leftover radiation from that early epoch. And I would say that it's kind of forgettable in this depiction. It's kind of boring in this depiction. And so as Slava mentioned to you at the very end there, we usually, instead of looking at its two-dimensional structure, quite a lot of the time, we look at it in this power spectrum space. And so I just wanted to give you a couple of little visual clues on how to interpret those power spectra in case you don't do it in your everyday life. So on the left there is a two-dimensional picture that has this one common length scale in it, just a bunch of concentric circles, and the length scale is how far apart the circles are. And so I did the math that's needed to make a power spectrum of that 2D plot, ignoring the phase or correlation information that Slava was showing you. It's possible to ignore when you have Gaussian fluctuations. And you get just this boring little peak on the right side. And the x-axis of the right side is what we call the amplitude of the wave vector. It's inversely proportional to the length scale. And so just to prove that to you, I took a picture that had a smaller length scale because the circles are close together. And you see that the peak for this one has moved over to the right. Let's see. See? Look at that. And indeed, if you then have a picture, the picture didn't need to be so regular. I just wanted to make it easy for your brain to do the Fourier transform and look at the power spectrum. So if you have something that just has a couple of specific length scales, like a plaid pattern where you have like the length of the side of the square and also the diagonal, then you can get multiple peaks. So then you get to the almighty CMB power spectrum, and it is amazing and not boring and not forgettable. It has all of those bumps and wiggles in it. And yet it's like a finite amount of cool richness, you know? It only has a few peaks and wiggles. And in fact, it can be fit with only 6 parameters. But those 6 parameters tell us information about the universe when it was only a few 100,000 years old, so we all get really excited about it. So what's plotted here is a power spectrum. It's just that the x-axis there, first of all, it's not a linear x-axis scale, but also instead of calling it a wave vector, we call it the multipole L. And for those of you who took physics at some point in your life, perhaps for many, many years, it's because instead of expanding in sines and cosines like I was doing for those other 2-dimensional pictures, you expand in YLMs, and so this L is the L of the YLM. But the x-axis is got, I don't know, 6 orders of magnitude in it, and that's because I wanted to cram on here not only the power spectrum that Slava already showed you of the intensities in that temperature map, but also start talking about the polarization of the CMB, which I'm going to say a little bit more about soon. And so those other plots are plots of the power spectrum of a map, which instead of being a map of the temperature is a map of how polarized that radiation is. All right, I barely need to do this because of the great introduction from Slava, but let me just try to give you this very quick explanation of what we think is going on. Why does the power spectrum have those nice bumps and wiggles in it? So here goes. So this is an explanation within the framework of inflation as explaining all the cosmic structure that we have. So the crazy thing about inflation is that it induced fluctuations in the dark matter density on scales. So you could picture like having one area of the universe where the density was high and one area where it was low. And the distance between those 2 areas could be larger. It could be superhorizon. What superhorizon means is the distance between those 2 points is larger than you would have thought information or light could have traveled in the universe given the age of the universe at that time. So since those 2 points, one where the dark matter density is high and one where it's low, since they're separated by a distance that's too far for sound or light to travel, then you don't expect the gravitational instability thing to start happening until the universe gets a little bit older, and then at some point the distance between those 2 points will be short enough that information could be conveyed between the 2 points, and at that point gravitational instability will start. And in particular, the plasma that the CMB is the relic radiation of, the plasma consists of, we always call them baryons, atoms and ions, we call them baryons. It consists of baryons and photons that are really tightly coupled together, and that plasma will start to slosh into, be sucked into these metric dimples that have just been revealed because, because time continued evolving. And then the photons and the baryons will get pulled in, and then the photons will get pushed back out by something called radiation pressure. And you'll actually get something like simple harmonic motion, the way a mass on a spring will bounce up and down. What else happens? Oh, right. The universe continues expanding, and eventually it cools off enough that the plasma congeals and the photons are separated from the atoms and the baryons, and that imprint is just left on there. So that's an explanation. Here's another possible explanation. Yeah, there was a Big Bang, and it's all been kind of anticlimactic since. Okay, and so one last thing, Slava already indicated this, but when you do fit these power spectra with that small number of parameters, you get information about the universe. So I indicated here, you get this conclusion that the universe is dominated by dark energy and has a lot more dark matter in it than it has ordinary atoms. Okay, let me say a little bit about polarization. And I took notes so that I could say it better. Okay, good. So what's shown in that left image is meant to give you an understanding of lots of things at once. Yay. So light comprises oscillating electromagnetic fields, which are propagating. And light is said to be linearly polarized if there's a specific direction in which the maximum electric field is larger than in other directions. And so there is an example here. So light traveling along this axis in this direction, I was trying to indicate the size of the electric field max. Here, it's small, and then in this upward direction, it's taller. So that wave would appear to a person who's sitting out here, that wave would appear to be polarized because the electric fields aren't in the same direction. But also contained in this plot is the fact that the light coming in from the sort of left and the top, neither of those light waves is meant to be look as if, I've run out of juice on this, I think. Oh, no. Is meant to be polarized because you see the electric fields look the same size in both directions. But there's this anisotropy or inhomogeneity in the field in these waves that are impinging on this electron that's sitting at the origin of the axis. And with that inhomogeneity, that's why this wave that comes out in this direction, so the waves are going into the electron from the side and the top, and the wave that comes out will be partially polarized. And for those of you who feel happy when I say these words, that's because the electromagnetic waves are transverse. And so there can't be any component of the electric field if that wave is traveling in free space. There can't be any component of the electric field in that direction. And so that's how you end up with this polarization. So it's a pretty generic thing that can happen in a plasma that where the light begins without being polarized, then it can, you can get polarized emission by this effect. And I think that's all I wish to say about it. Because now I want to show this plot. If you are an experimentalist like I am and you want to know whether the light that's coming towards you has its electric field larger in one direction than another direction, there are very specific techniques you can use. You basically use a detector that is sensitive only to electric field in this direction, and you could imagine that then you rotate that detector around and you say, when did I get the biggest signal? And afterwards, you'll know the direction of the polarization. And then you can draw that on the map of the area that you were looking at, just in terms of a bunch of lines, as is done here. So there's this special type of pattern that you could get where the lines, if you considered a single direction in space, that's this k-vector direction, you might see a pattern where the polarization gets bigger and bigger in the vertical direction, then it starts to get smaller, and then it switches to being in the horizontal direction, and it gets bigger and smaller. Kind of messed up the pattern here, you might have this kind of uniform oscillation. For those of you who like to talk about Stokes parameters, that would be like a sinusoidal variation in the Q Stokes parameter. But another thing that you could have would be something where the light appears to be polarized at plus or minus 45 degrees relative to that k-vector. Oops, that's not what I wanted to do. Relative to that k-vector axis. And it turns out that that acoustic oscillation phenomenon I was talking about, where there were the superhorizon dimples and the baryons and photons were getting dragged in and pushed back out, that whole thing, it only gives you patterns of polarization of this flavor with this type of look. And we call those E-modes. And so in the picture of the power spectra, this was the E-mode power spectrum. And this was the other kind, the plus or minus 45, and I'm going to say more about that in just a quick sec. And I forgot to say one other thing. Not only are there data points from the Planck satellite on these black lines that are the model, but all the different colors are from other experiments. And so there's that have different abilities and can complement Planck in certain ways. And what you can see here is that there's great, sort of astounding agreement among all of those experiments. And I've been doing these measurements for such a long time that I can tell you it wasn't like that in the beginning. There was a lot of disagreement in the beginning. Okay. Oh, so this was just showing you sort of a a mathematical way of distinguishing between the two E modes and B modes in terms of a symmetry property, which is that you can reflect the top pattern about the K vector, which is indicated with the dashed blue line. You can, no, you can't. Yes, you can reflect it and it won't change, so it's got an even symmetry. But the bottom one, if I reflect it up and down around that purple line, it does change, it looks different, so it has an odd symmetry. So sometimes we say the B modes have this odd symmetry. But the really important point is that that acoustic oscillation phenomenon only produces the E mode type. Okay, but here's the thing. Primordially, back when the universe was only a few 100,000 years old, there were only E modes. But something happens as the photons try to get here from that earlier epoch. That's what photons do. They just travel at the speed of light throughout the age of the universe until they have the pleasure of being detected by, hopefully, a detector that I built. So what happens is that if there were no matter in the universe, and remember, Einstein says matter can bend the fabric of space-time. So if there were none, then the light ray from a specific point from the CMB would just head straight into the telescope. And, but if there's some chunks of intervening mass, then the photon will have to curve around that mass. And then when the hapless astrophysicist like myself is trying to figure out where that light ray came from, the way you do that is just by assuming it came to you on a straight line, because you don't know what curved line it could have come on. And so now you think it came from a different point. This is greatly exaggerated, but in terms of how far apart the deflections are. The deflections are usually about around a couple tenths of a degree, 1/60, a few arc minutes. But anyway, this rearrangement doesn't respect that original symmetry in the polarization, and therefore you can get this lensing signal. You can get apparent B modes that are really just rearranged E modes. But we understand enough to understand what the shape of that B mode curve, the lensing B mode curve would look like, and it looks kind of like this. Okay, but finally getting to the excitement, the oldest gravitational waves in the universe, it is here. Gravitational waves that might have been produced in that early epoch of cosmic inflation, they would still be propagating through the universe, because what would stop them? And those gravitational waves, they have this property that they alternately stretch and compress space, and when they do that, they also can make quadrupolar patterns in the plasma that will cause the electrons to emit polarized radiation, but that radiation doesn't have to respect that original even parity. So you can get both E modes and B modes from gravitational waves, and then it's very exciting to try to look for them. And there is already a known possible shape. So this is that lensing shape here, but then you can get these other small signature curve, and if you could measure those, and then you would be measuring primordial gravitational waves, and might tell you something about inflation. You seem to be standing up as though I've been speaking for 26 minutes. Okay.
4 minutes.
Okay. Oh, it felt like 20. Okay. So if you could detect those, it would be pretty amazing. Some of you who read, say, the New York Times may know that in 2014, some colleagues of mine believed that they had detected the B modes, but it's a very difficult process. The signals are very, very small, and that discovery turned out to be false. But there was quite a lot of excitement at that time, and then that same team had very good instrumentation, and they've continued to use it and build on it. And so they've set the best limits so far on but have not detected any B modes. So let's see. Oh, I have a whole bunch of super cool plots and an unnecessary zoom. But I will move through them because Bill is probably uncomfortable having to stand like this. So I just want to talk just for a quick minute about how it's kind of hard. I'm not going to whine. I'm going to talk to you about the joy of responding to the challenge of experimental physics. But how it is pretty hard to try to measure these B modes because the signals are so small. And you have to worry about instrumental systematics. You have to worry about signals from foregrounds, including our own galaxy and that lensing signature. You have to worry about contamination from the local environment. And you just have to build zillions and zillions and zillions of detectors and telescopes in order to have enough sensitivity to measure these small signals. And the data sets get complicated and somewhat hard to analyze. I really wanted you to understand that the atmosphere gets in the way. It absorbs microwaves, and that makes our lives quite challenging. And it's why, in case you wondered, CMB experiments tend to either be balloons or satellites or in very high dry spaces, like at 17,000 feet in the Atacama Desert in Chile, the place I like to build things, or at the South Pole. And this is shown because there's less water in those places than others. And really, Bill, I am almost done. There's emission from the atmosphere. You can have more or less emission depending on how wet it is. That is, the x-axis here is the frequency of observation. So it shows you that some frequencies are harder to measure than others. It messes up lots of other things, too. You have to build lots of detectors. This is what I was kind of going to spend the whole talk on, because it's what I spend my whole life on. But instead, I'll just let you see some pictures. That's me. I'm the punching bag, not the really fit woman. You have to build really cool optics. You have to use dilution refrigerators. They are so cool. And the quantum mechanics world gets to use them, and so do I. It's hard. You have to go to big sites. And then finally, there are problems that of course, you haven't dreamt of when you first start the mission. I can't go backwards, Bill, you're so lucky. Oh, so there are problems you haven't even thought of when you get started. And so I'm a millennial, and so I think in emojis, and these are like the emojis that I've had whenever we hit these difficult problems. And the main thing is you fall down 7 times and you get up 8. So that's the end, so thanks a lot.